Welcome to Signals and Systems subject classes. Now we're in the 7th chapter, that is Laplace transform. So in this chapter, this is the first video. So we are going to start the new technique, that is Laplace transform. So you should remember, so this Laplace transform, it is related to the continuous time signal. So this x of t, it is a continuous time signal. So continuous time signal. Here, I would like to explain this Laplace transform from the Fourier series onwards. So again, we should go back the continuous time Fourier series, then and continuous time Fourier transform. So what are the differences? So what are the advantages? What are the drawback overcome by the Fourier transform? That each and everything we have to discuss. The first of all, you know very well. So this Fourier series, so continuous time Fourier series, continuous Fourier series. So it is for converting the time domain to the frequency domain, that you know very well. So but the signal must be periodic. It cannot be applied for the aperiodic. So x of t, so it is a periodic. So continuous continuous time signal, and also it is and periodic. Periodic signal. So in Fourier series representation, any periodic signal can be represented as. So this is Fourier series representation. Already we discussed this one in detail. So this is it is nothing but summation of the exponential. So that equal e power jk omega naught into t, k from the minus infinite to the plus infinite. So this Fourier series coefficient, so ak, it is for equal to minus t by 2 plus t by 2. Why? Because this x of t is a periodic. E power minus jk omega naught into t into dt. So here omega naught, so fundamental frequency, that equal to 2 pi by capital T. Capital T is nothing but time period of the x of t. So this is about continuous time Fourier series. Would it write? This is continuous time Fourier series. Is it? So it is applicable for the periodic only. Periodic only. So that's why. So it cannot be applied for the aperiodic, for the conversion from the time domain to frequency or frequency domain to time domain. So this is conversion x of t periodic for the conversion. So Fourier series, then so this is about continuous Fourier series. So so it is cannot be applicable, cannot be applied for the aperiodic signal. So that is the main drawback of the continuous time Fourier series. To overcome that one, we went to the continuous time Fourier transform. Continuous time Fourier transform. Transform. Already this continuous time Fourier series and continuous Fourier transform. So it is discussed in the previous classes. So this is the chapter 2. This is chapter fourth one. So this is chapter 3. This is chapter number 5. So here, this is discussed in the chapter 3. So this is in chapter 5. So in continuous time Fourier transform, see, we are considering that Fourier transform x of j omega. You know that here, so this x of t, so it is aperiodic. So it's Fourier transform x of x of j omega. So this x of j omega is nothing but ak into t. So x of j omega that equal to, so minus infinite to plus infinite. This time period, actually in the derivation we are assuming that is also x of t also periodic, but it time period equal to infinite. So these are the infinite time periods. E power minus c, we have taken the k omega naught equal to omega. Then so k omega naught equal to omega t into dt. So in this case, so x of the real part equal to 0 plus j omega. So the real part, for example, sigma equal to 0. So real part equal to 0. So inverse Fourier transform of the continuous time signal that equal to x of t 1 by 2 pi integral of, so minus infinite to the plus infinite. So x of j omega into e power j omega t into d omega. J omega t into d omega. So, so this is for the aperiodic, aperiodic. The special case is only aperiodic, periodic and periodic also. The mainly it is used for the finding the time domain to frequency domain for the aperiodic signal. See, so here in the continuous time Fourier transform, after applying this formula, you will get the function. So this is the function. But in this function, we are considering real part equal 0 only. It will have the only imaginary part. If you want to draw this one poles, you will get different values for the omega. So this is S domain, or so this is the real part. We are taking the real part on the x-axis, imaginary part of the y-axis. So after applying the Fourier transform to the continuous time, we will get the function of j omega. So all values. Why? Because here we're considering here this is so this is sigma. The sigma equal to 0 here. This is sigma equal to 0. Sorry. So we're considering sigma equal to 0. So this is sigma. So automatically, if you want to draw, represent the poles and the this sigma and j omega plane, this is then all poles will be appear on the y-axis. So this is poles on the y-axis in the case of the continuous time Fourier transform. So it never occupies the this first coordinate, second coordinate, and third coordinate, fourth coordinate. It only lies on the imaginary axis. So this is imaginary axis. For example, this is S domain. In S domain, this S value is nothing but sigma plus j omega, real part and imaginary part. So this is the real axis. So in real axis, so it never cover the total area, first, second, third, fourth. Then it is difficult to find the stability. The major point is, so the major stability cannot be decided. So this is the main drawback. So that's why you are going for the Laplace transform. So that is Laplace. In Laplace transform, the variable is S. See, so here the variable is S. So this S is nothing but S equal to sigma plus j omega. So if you consider the sigma in this function, in this continuous Fourier transform, so in this here I am see, this is continuous time Fourier transform equal to x of j omega, that equal to integral of minus infinite to the plus infinite x of t into e power minus j omega t. So in this case, in the continuous Fourier transform, sigma is considered as 0. Now, if you consider the sigma value, so now I'm taking the sigma, considering into the equation. So sigma plus j omega. So that equal to, so sigma, sorry, integration minus infinite to the plus infinite x of t e power minus j. So, sir, j omega, it's not j omega. So minus of in place of the j omega, we should take sigma plus j omega into t into dt, differentiation with t. So here we're considering sigma plus j omega, this is a variable that is s value. Then, so x of, now replacing the sigma plus j omega by the s, so x of s that equal to integral of minus infinite to the plus infinite, so that equal to x of t into e power minus s into t dt. So this is nothing but Laplace transform. So we have taken the sigma plus j omega equal to s. So this is very, very important. So x of t, so Laplace transform. So Laplace transform, that is x of s. So this is about Laplace transform equation derived from the continuous time Fourier transform. So in this case, the poles of the x of s, it may be covered throughout the s domain coordinates. So this is about Laplace transform. Then we will do some problems. So problems on the problems. So x of t, continuous time signal x of t, here I am taking one e power minus a into t e of t. Then the Laplace transform of x of t is what? Is it? So the Laplace transform, so x of s is equal to integral of minus infinite to the plus infinite. So equal to x of t into e power minus at into e of t. Sorry, actually I want to write a formula. E power minus s into t into dt. Now substitute. So x of s that equal to, so this is the function, it will have the magnitude for the positive values only, from 0 to infinite. So there is no signal from the minus infinite to 0. So that's why, so take the limits only 0 to infinite. So e power minus a into t. So e of t will be 1 into e power minus s into t into dt. So that equal to integral 0 to infinite e power. So here e power, then we can take the t common, then a plus s into t. Now do the integration. So in this integration, so exponential function integration e power x, integration e power x. Then there is a constant. So here I'm taking the constant minus s plus a into e power minus s plus a. So limits are 0 to infinite. So this is a very, very important step here. So minus 1 by s plus a. So previously, while calculating continuation of Fourier transform, in that case, we got here j omega. J omega is a complex. For the complex, we ignore that complex number. But in this case, it is having the realigned complex. For that case, if so, we are going to substitute here. I am writing here e power minus s plus a into infinite minus e power minus s plus a into 0. So we know that e power minus something into infinite, or sorry, e power minus infinite, it goes to 0. So it must be minus. Already here minus is there and infinity is there. Then this value must be positive. Positive. That is the condition. So in previous case, in continuous time, that is a j omega, then we neglected that one. Why? Because a is automatically positive. We have taken here. So this is a is a positive. So in that case, a automatically positive, then we ignore the j omega. But this s having the real value, so we should take the condition. What the condition? The real part of s plus a must be positive. Must be positive. Then only it goes to, so minus 1 by s plus a. So for that case only, for this case only, it goes to 0 and minus 1. Then we will get that's x of s, that equal to minus 2 minus plus 1 by s plus a. So we are getting this value for the condition. The condition is what? So real part of s plus a greater than 0, or so real part of s greater than minus a. So we know that real part of s, that is we denoted by the sigma, then we can write sigma greater than minus a. So from here, see, here I'm writing this x of t equal to e power minus at into e of t, the comma, a is a positive. For this case, the Laplace transform, so just L is enough, Laplace transform. So Laplace transform, that equal to what? Here we got 1 by s plus a and sigma greater than minus A. So this is called ROC, region of convergence. So this is a very important region of convergence. In the region of convergence, so for this condition only, the sigma must be greater than minus A in region of convergence in the S domain. In S domain, just this is sigma and j omega. So this is, I'm assuming this is minus A. So the sigma, the real part must be greater than minus A. So this is a region of convergence. For this case only, this 1 by S plus A defined for this x of t. So it is called region of convergence. This is region of convergence. This is very important. We will see another problem. Then you will understand what is the region of convergence. So another problem. So, see the continuous time signal x of t equal to minus e power minus at into u of t, u of minus t. So this is left-handed side signal. For this, so what is the Laplace transform of x of t? So that is we can denote by the x of s. So this is the question. So in this question, so the Laplace transform, so x of s, so that equal to integral of minus infinite to the plus infinite. So x of t into e power minus s into t into dt. Now substitute that one. So this is, we know that u of minus t is a left hand side signal. So it will have the magnitude from the minus infinite to 0. So So minus infinite to 0, that is minus e power minus at into e power minus st into dt. So here I'm writing, so minus infinite to the 0, so e power, so in this case minus a plus s into t into dt. So minus, so integration e power minus s plus a into t by minus s plus a. Limits are, so limits are minus infinite to the 0. So this minus minus gets cancelled. So 1 by s plus a, substitute, so e power minus s plus a into 0 minus e power minus s plus a into minus infinite. So the next step, so 1 by s plus a, for understanding only I'm writing all steps. So e power, then next time I do not write all steps. So these are very, very important. Up to 2 or 3 problems, I'll write all steps. So minus, so this is it goes to 0 minus e power. See this minus into minus plus. So s plus a into infinite. So if s plus a is a positive, it goes to overall value goes to infinite. So it is not convergence. For the convergence, s plus a must be negative. So the real part of s plus a must be negative. Then only s plus a, so it will be 1 and it will be 0. For condition, so sigma plus a less than 0. So that x of s, we are getting the Laplace transform that equal to 1 by s plus a, the condition sigma less than minus a. So already I told you, so this is called region of convergence. Region of convergence. So we understood that. So minus e power minus at into e of minus t. So its Laplace transform. It's Laplace transform. What we are getting here? So 1 by s plus a, the condition sigma less than minus a. So in previous case, we have taken e power minus at into e of t. Its Laplace transform. So its Laplace transform also, it is equal to the 1 by s plus a, but the region of convergence is sigma greater than minus a. So how to remember? So this is sigma greater than or less than. See, so this is, okay, After writing the region of convergence, I tell you. So region of so this is minus A. So sigma, see, so this is sigma less than minus A. So the sigma values, sigma, see, this is the case for the only sigma values. So we are not considering any omega values, is it? So, so sigma less than minus A. So this is the minus A less than values. So this is, so it is about region of convergence. So here, says e power minus 8 u of t, this is greater than sigma. So this is the right side. So right side signal, right hand side signal. So it is also automatically, it is also right hand side, is it? Right hand side. Sigma greater than, so sigma equal. So because of this minus a, so here this minus a, here we are getting this minus a. So this is left hand side signal, left hand side. So this is our sigma less than minus a. This is also left hand side region in S domain, left hand side. So this is here minus a and minus a. Then you may get doubt. So I will do the problems. So like then we will come to know that the difference. So problem. So one is x of t. So x of t. Now I'm taking e power at into e of t. Then its Laplace transform of is what? So directly here I'm writing integral of, so this is the right hand sided, so 0 to infinite, so e power at into e power minus st into dt. This is about Laplace transform. So integral 0 to infinite. So e power. So t is a common. So a minus s into t into dt. So 1 by so a minus s. So e power so a minus s into t. Limits are 0 to infinite. So 1 by a minus s. So now this is e power a minus s infinite minus 0. The condition here, sorry, this is 0 after substituting 0, this is 1. 1 by a minus s, so it will be 0 and minus 1. For what condition? A minus the real part of s must be less than 0. Then a less than the real part. So this is the case. So take the minus common, then the minus minus gets cancelled. So the answer is 1 by s minus a and sigma. So this a less than sigma or sigma greater than a. So this is the x of s. Sigma greater than a. And another problem. So this x of t minus e power at into u of minus t. It's a Laplace transform. So in this case, I'm directly right. So x of s, so it is having the magnitude for negative. So minus infinite to 0. So this minus e power at into e power minus st into dt. Then minus e power a minus s. Then it is better to write minus s minus a into t. So this integration same, but we should divide by the minus s minus a. Limits are minus infinite to the 0. So minus minus gets cancelled. 1 by s minus a. So this is it will be 1 and minus 0. For what condition? Already this is minus infinite. So minus into minus plus. So plus infinitive. So this must be negative. So this s minus a, sorry, region of convergence. So real part of the s minus a, that must be negative. So negative. See, minus minus gets cancelled, infinite. Infinite, this s minus a, it must be negative. So s minus a, it's a negative. So real part of, so in final step, we are getting so x of s equal to 1 by s minus a. So real part less than real part, this is real part, less than a. So coming to the region of convergence, so ROC, so ROC for this 2, In the first case, this is the for the 1 by sigma. This is sigma greater than a. This is sigma less than a. So this is a. This is a. So sigma greater than a. So this is the region of convergence for the 2. So in finally, I would like to write all these equation in one place. See, e power first, e power minus at u of t. So it's Laplace transform. So Laplace transform. So Laplace transform that equal to 1 by a. So here this minus a, you should write this is s plus a, and this is the right side. Right side, so right side, so sigma greater than, what is it here? Here minus a. Is it? Next, e power minus at into e of minus t. For this case, if you, there is no minus, for example, there is no minus. So this is, so Laplace, so you will get minus 1 by s plus a. So I want to show you these two are having the same Laplace. So for that case, I want to take the minus here. So for that, here also we will get the same Laplace, but the region of convergence is different. So this is left sided, so sigma less than. So what is the here? What is the coefficient multiplication for the t? Minus a. That's you should write minus a. Next one, e power at into u of t. So what is the difference here? Minus a, here minus at. But there is a change. See, this is so Laplace 1 by, so s plus a. What is the a here? The plus minus a. So s of, so plus of minus a. Then minus a. So this is right sided. So sigma greater than, for the right sided, you should take the greater than. And what is the coefficient multiplication for the t? A. Just right here. So minus e power at into e of minus t. It's Laplace transform. So that equal to Laplace transform. So that equal to 1 by s minus a. There is no change, but there is a change in the region of convergence. So this left hand sided, so write less than, and here this plus a. See. So this is about Laplace transform. It's very, very important. It's very easy to remember also. So there is a lot of chances to confuse, to remember this formulas. So this is about Laplace transform. Then in next class, we will do some more problems, and we will derive the formula for inverse Laplace transform in the next class. Thank you.